All right, so you've got your assignment that's due about now. And PS6 will come out tomorrow. And then there won't be a PS7 for a while because there'll be a midterm. So after the week after PS6 is due comes the midterm, which is February 28th. So it's 2 weeks from today. It's in class. You can bring one sheet of notes. It'll cover everything we've done through today, including include everything we do through next week. No, take that back. It'll cover what we do through today, including PS6, which is due next week. I'll put up a sample, an old midterm for you to look at. And then there's just another week of classes after the midterm, I think, until spring break. Or maybe it's 2. Anyway, yeah, spring break's earlier this year. Anyway, it's coming up soon. Any questions or problems? Yeah.
Is the note sheet you're doing two-sided?
Yeah, two-sided, handwritten, or printed out, whatever. Any other questions? Yeah.
For the CADIS assignment this week, when we're printing out each day's people that we're supposed to print the report, do they need to be in any specific order?
Yes, alphabetical order, or lexicographic order, technically speaking, but it's just the normal sort that you get in your programming languages. Any other questions? Well, I want to talk about the CADIS problem just a little more. Oh, that's not right. All right, so I've had several people ask me, actually right before class, are we doing a standard breadth-first search to solve this problem? The answer is yes. You don't have to modify the breadth-first search at all. You do a breadth-first search, and you get an output like you see on the screen there. Okay? Now, once you've done the breadth-first search, you've gathered the information you need to produce the output. How can you produce the output? How does the distance array govern the output? What output should we have for this tree? Yeah.
We just group and sort things that have the same distance values?
Right. So we take everything that has a distance of 0. That's the person that started the rumor. So they get output first. Then what gets output next? Yeah. Okay, so then the 3 that are 1 distance, so you do the breadth-first search to find out distance from the root. So next come B, E, and F in alphabetical order. Okay? And then all the 2's come out, and there's only 1 there, so C would come out next. And then D and G come out in that order. And then H, and finally, oops. I'll do H, and then I. Comes out last. So that's the output. Now, can you produce the output as you're doing the breadth-first search? Like you visit a vertex, you output it. Does that work? No, because at each level, you need to do the output in alphabetical order. So you have to at least see the whole level before you can do any output. So you could do something like that. You could complicate the breadth-first search algorithm to notice when it's starting a level and when it's finished with a level, and at that point stop and sort and output. But it's simpler just to run breadth-first search and use a distance array to govern how you format the output. Now, having said that, let me propose an algorithm for producing the output, and you tell me what you think of it. So I have my distance array. I'm going to scan the array and find all the zeros and collect them into a list. So that will be A. So basically, scan the array. Is that a 0? If so, copy over the A. If it's not, keep going. So, and then I'm going to sort that and append it to a string. So now I've got a string with A in it. Then I'm going to scan it again looking for the 1s. And that'll get me the B, E, and F. I'm going to sort them and append them to my string and get B, E, F. Then I'm going to scan again, looking for all the 3s. And I find C and G, so I append C and G to my string. And then I scan again and again and so on. So first of all, how many times do I need to scan for an R? For this one we can see I got to scan it for the 0, the 1, the 2, the 3, the 4, and infinity. So I have 6 scans. How many scans in general would you have to do if they're V vertices? Well, right, but how many arrows would I have to draw here? How many scans? So V, maybe it's V plus 1, V minus 1, I don't know, but roughly V. So what's the problem with this approach? Yeah. It's V squared. Yeah. So you've taken a really efficient breadth first search algorithm that runs in linear time. You blast through it, generating this distance array, and then you're using a quadratic algorithm to produce the output. Now, I didn't get this, I didn't think of this myself. I was curious yesterday, and I was poking around the Caddis queue, and I saw solutions that were running out of time, and this was why. So the larger lesson is going to be, you may sit in the class and you think, I'm never going to have to write in my life something to find strongly connected components of a graph. Why does any of this matter? And you're probably right. You're probably not going to write a strongly connected component algorithm or need to use one. Some of you may, but most of you won't. All of you are going to write doubly nested loops over and over again. You need to have enough awareness of algorithms and complexity to realize that doing that's a bad idea. And I suspect that when you do something like that and you start looking for why your program is too slow, you're looking in the wrong place. You're thinking, you're not suspecting, it's just this output production. You're probably looking in the breadth first search. But that's not where the problem is. Now, let me tell you another thing. What else is bad about the way I'm doing the output, besides the scans it takes to find the letters? Yeah?
I mean, you're already essentially doing this once. You're already choosing the sections, and then you're going and finding the sections the second time. Or you're doing the breadth first search, you can just put the rest of the arrays the first time.
Well, you could put them from the breadth first search. You could put them in the array the first time, but it's a little tricky to get them in the right order during the breadth first search. But suppose that we found a fast way to identify, the letters in the right order. There's another thing lurking about the way I'm producing the output. Yeah.
Does it have to do with appending?
Yes, it has to do with appending. I see this a lot too. You've got a bunch of things you've got to output. So you find the first one, you make a string from it. You find the second one, you append it to that string. You find the third one, you append it to that string. Append, and finally you print the string. That's in the quadratic algorithm as well, because every time you append, append is misnamed. What happens when you take a string and you add on to the end of it? Yeah.
It makes a new string.
Right, it copies the original string and sticks the new thing on the end. So you've got a loop now that is producing ever longer copies of strings. So the first append is cheap, the next one's more expensive, the third one's more expensive, and so on. It's n squared. That's another thing that can kill you. I see students that need to know whether something is in a list, and so they use contains method. That's linear time. Use a set. So these complexity issues come up all the time, but you won't recognize them unless you're practiced at it. So what would be an efficient way to, first of all, in the world of Caddis, what would be a better way than constantly appending to a string to generate output? Yeah.
String builder.
You could use string builder. Is that what it is in Java, or is that C#? There's something similar in Java. Same name. So that's a mutable string. Or you could just output it. Instead of building a string, just send it to the output. What would be another way to approach this, to get things to come out in the right order. Again, using just plain old breadth first search so that you get you get the distance array. Yeah.
Implement your own sorting logic and just sort the array.
Right. Just implement your own sorting logic. Just imagine sorting an array of entries where when you compare two elements, what it does is it compares their distance in the distance array. And if they're tied, it uses alphabetical order. So basically a custom comparator to sort the array. So in the case of your caddis problem, this distance array is going to be a hash table of some kind, right? It's going to map from names to distances. So you just take an array of all the names and sort it with a custom comparator, which a comparator pays attention to this number and to the actual string. I mean, there are lots of ways to do it, but you gotta be aware there's a problem before you can solve it. Any questions I could answer other than what I've just done? Yeah.
So are you saying that it is better to overload like equal to functions or less than or greater than functions to compare for a sorting algorithm?
Well, in Java and C#, when you sort a list or an array, you can pass in a second parameter, which is, in C# would be a delegate that you use to compare the elements. So just write a delegate that knows how to compare strings by looking them up in the distance array. And if necessary, actually comparing the strings. That way you just do one sort at the end and you're done. Instead of having to work really hard to sort little bits of different arrays. The key is to avoid the n-squared work, the quadratic algorithm. That's what will kill your time. I mean, some of these caddis problems are designed so that if you don't use an efficient algorithm, if they're designed so that if all you do, let's say the problem size is n. If all you write is a doubly nested loop that goes I equals 1 to n, j equals 1 to n, and does nothing else, it'll take too much time just to run those loops that don't do anything. Okay? That's how picky they are about the time required. Okay. All right, last time we were talking about Dijkstra's algorithm. And this is it. And you remember I remarked on the real similarity between Dijkstra's algorithm and breadth first search. The big difference being that whereas breadth first search uses a cube, first in, first out cube, to keep track of the fringe of the search, Dijkstra's algorithm uses a priority cube to keep track of the vertices that are on the fringe. That's one big difference. The other is what you actually do inside the inner loop. Is somewhat different. This is a different problem. But just to remind you how it all works, I'll go through. We did this animation before, and I'm not going to spend a lot of time on it here. But the idea is that Dijkstra's algorithm starts with a previous array and a distance array that's initialized like that. You start by putting the start vertex where your search is starting from on the priority queue, and then you enter a loop. And in the loop, you're always pulling the item with the smallest weight off the queue. So A has a weight of 0, so I pull it off the queue. And now it's been incorporated into our shortest paths tree. All right, what do we do from there? Every time that you pull something off the priority queue, what do you do with it? Yeah?
Mark it visited?
Yeah, certainly. Well, does this mark visited? This one doesn't mark visited. How do we get away without marking it visited? How do we know we're not going to visit it again? Yeah.
Because there are no negative paths, so it will never be shorter to get back to something.
Right. Anytime we attempt to go back, suppose there was a loop back to A. We're going to hit this inequality eventually. The only time we'll revisit something is if there's a shorter way to get to it than we do before. And since there are no negative paths, we're not going to find a shorter way to get to A than 0. So we really don't have to use a visited array. It just turns out we won't once we take it off the queue, there's no way for it to get back on. Okay, but what do we do with that thing now? Now that we've colored it yellow. Yeah? Right. We look at all of its children. We basically look at all the children and consider whether or not to put them on the priority queue. Now, in talking to people about another of the problems this week, I found out there's a fair amount of misunderstanding about this pseudocode right here. This pseudocode isn't saying find every edge in E. What does this pseudocode say? Yeah.
Every edge originating at U.
Right. Find every edge of the form UVW. Well, we know what U is. U is known. So we're finding every edge that starts with a particular value of U that goes to some vertex and has some weight. So basically we're pulling out V and W, not U. And that's notation I've been using all throughout. Just so I'll make sure everyone knows. So in turn, we look at every edge out of A. And how do we decide whether or not, so this time we're going from A to B, how do we know whether to put B on the queue? What's the fundamental thing we're looking for? Yeah?
The distance comparator?
Right. We know currently our distance array has the shortest known distance to B, which is infinity. And we want to see if, suppose we go take this path directly from A to B, is that going to be shorter? And we say, yeah, the distance to V, in this case, V is D, so the distance to B is infinite. And that's greater than the distance to A, which is 0, plus the weight of that edge, which is 2. So we found a better way. So we update the graph and put the B onto the priority queue. Okay, so now we know there's a way to get to B that only costs 2. We go via A. And then the same thing happens with E. It gets on the priority queue. And the same thing happens with F. It goes on the priority queue. So at that point, we've got the tree vertex, which is the yellow edge. We've got the fringe vertices, which are the ones that we have encountered so far. And then the ones in white are the ones we haven't found out about yet. All right, so we're done with that loop. So again, we pull B off the queue. Now, once B comes off the queue and becomes yellow in my diagram, you notice I also made the edge from A to B yellow. That just means that we're not going to find, that is the way you get to B, is from A. We're not going to find a shorter way. That's baked in. Those orange edges, the purple edges are subject to change. In fact, we're going to find a shorter way to get to F. We're going to find a shorter way to get to E, but we're going to find it before they come off the priority queue. All right, now we consider all the edges out of B. So there's that one from B to C, and that's better. Infinity is greater than 3, because we know how to get to B in 2, and then we can go from B to C in 1. So we're going to update I got kind of lost here. Okay, so C goes on the queue, and C gets updated in the distance in previous arrays. Then we consider F. So what? Have we improved? We currently know how to get to F in 4. Distance to B is 2 plus W is 1, because we're looking at that green edge. That's better. So we're going to change B. You'll notice the entry for B in that array up there is going to change shortly. It's going, okay, at some point it changed there. I wasn't looking. Anyway, I looked at the wrong thing. It's F. Okay, F changed to 3. Let me back up. Okay, before, the previous of F was A, and the distance to F was 4. And it's changed to B in 3 now. And furthermore, look down in the queue. F did have a weight of 4. Now it has a weight of 3. So we updated the thing on the queue. So the weights can change in the queue. They just don't change once you're out of the queue. So that's all the edges out of B. So again, we pick the lightest thing, which would be either C or F. We could pick either one at this point. I just picked C. We're going to look at all the edges out of it, and it's going to new territory. So both of those are going to go into the queue for the first time. So there's D. D goes on the queue, and there's G. G goes on the queue. And then we're done. We pull F off, and the game continues. Yeah?
The distance is the same distance from A, right?
The distance is, The distance is distance from A.
So if you could run it starting at a different vertex and that would change the
Yes. So for example, what would happen if we did what if we started Dijkstra's algorithm from I? It would find the shortest path to D is 4 and the shortest path to H is 3, and that's all. It wouldn't be able to visit. It's just like breadth first search. If you start a breadth first search at I, it would only see P and H. Yeah.
So, every vertex can only go in the priority queue once, right? Like once it's
Right.
off the priority queue, it will never go back on it.
Right. A priority queue comes on a vertex comes on the priority queue. Now, while it's there, its weight may change.
Of course.
But once it comes off, it's not going back on
Yeah.
because there's no negative edges.
And
It turns out.
so is that unique to Dijkstra's algorithm? Like, would a general breadth first search algorithm?
Well, it's not breadth first search; it's shortest path algorithm.
Okay.
Well, I mean,
it's
yeah. For example, if we took, if instead we used Dijkstra's algorithm and allowed negative edges,
then it would potentially go back on.
right? Then you might imagine there was a gigantic negative. Well, we've already been through this.
Yeah.
And I keep messing up anytime I try to show you. But with negative, you can end up with negative edges even without negative cycles, and you can end up finding shorter paths, not back to the root, but to other places
Okay.
that cause the thing to go back on the queue.
Okay.
And it will eventually, what will happen with Dijkstra's algorithm with negative edges like that is things will go back on the queue and then come off and go back on the queue. It'll settle down to the right answer,
Right.
but it may take a very long time. You could set up a graph that would take exponential time.
Okay.
Any other questions? Yeah.
So last time you said that if someone could come up with an efficient algorithm for a graph with negative edges and cycles,
They
that
would.
would be good. What does efficient mean in this case?
Okay.
What kind of runtime?
So what I said last time is, think of the general problem of, okay, typically when all of our algorithms, we've assumed for all of them, there are no cycles of net negative cost. So suppose you remove that restriction. Well, the problem with removing that restriction is the problem is not well defined now because you can end up with a situation where there is no shortest path between two things because there's a negative cycle you can go around any number of times. But suppose we change the question now to find the shortest path in any graph subject to the restriction that it can't follow any cycles. It has to be a cycle-free path. So that problem is NP complete. And what I said was that an efficient algorithm would be a huge shock if anyone found it. By efficient, I mean anything less than exponential time. O of n to the 100th would be earth-shattering. Yeah. Any other questions? All right, so I'll skip through the rest of this here. More of the same. All right, so let's analyze Dijkstra's algorithm and see how efficient this is. So we've got the initialization block up there. So what's the complexity of that? That first, the for each down to distance s equals 0. Yeah? Yeah, that's O of V. Depends on the number of vertices only. We got to create the priority queue, and that's going to depend maybe on what kind of priority queue we use. So I'm just going to say right now I'll just leave that unbound. It's going to cost whatever creating costs. Then we do that single insertion of 0, and I'm going to call that the cost of inserting into the priority queue because that will depend on the representation. Now, how many times do we do that loop test while the priority queue is not empty? Now, I've heard an E and I heard a V. Think about that loop. Every time through the loop, what happens? The queue's not empty and something comes off the queue. But since vertices can't ever go back on the queue, the most you can do is take every vertex off once. So that's going to be, you can do that V times at most, and the cost of that is whatever, V times the cost of that empty test. So we'll have to figure out what the empty test costs later. We're going to do a delete min. How many times are we going to do a delete min operation? V times. So it's V times the cost of a deletion. We're going to have to enumerate all the edges. and we've seen this trick before, the amount of work it takes to find all the edges out of U is going to vary from depending on how many edges there are. But over the life of the entire while loop, you've got to consume the entire data structure. So that's the cost of, it's basically proportional to the size of the data structure. And how many times are we doing the update operation? This part right here. If distance of v greater than distance of u plus w, and then the two that follow. What would be the worst case for how many times you update? When you update, you're updating an edge. You're using an edge to do an update. Yeah? O of E. But O of E. And similarly, how many times, if we can do the update O of E times, we're going to do that insert or change operation E times as well, at most. So that's O of E times the cost of insertion. So that accounts for everything. But we've got some unbound variables up there. The cost of creating an empty priority queue, a cost of inserting into a priority queue, the cost of testing whether a priority queue is empty, the cost of the delete min, plus the cost of enumerating all the edges. So if we gather all the terms here, we get that. I gathered the terms and eliminated the obviously smaller terms. Okay, let's make some assumptions. I claim that it shouldn't be too hard, no matter how we represent the priority queue, to test whether it's empty in constant time. Surely we can keep track of the size and just do that. So I'm going to do that. And I'm going to assume, remember my create operation takes as a parameter the maximum size the priority queue is going to get to. So and that is V. So I'm going to assume that we can create a priority queue that holds n elements in time proportional to n. So those are our two assumptions. We can create the empty priority queue in O of V time, and we can test for empty in O of 1. If we do that, the O of create now is a low order term, and the O of empty is a low order term. So we end up with V times delete cost plus E times the insert cost plus the cost of enumerating. So on a matrix, it turns into that. Because the cost of enumerating all the edges is V squared. Now, if you got to design the priority queue and you wanted to make the complexity of Dijkstra's algorithm as low as possible in the case you were using an adjacency matrix, what would be the maximum complexity you'd be willing to use for delete? Well, yeah, I'd like delete to be V so that V times delete would be V squared. Okay? So I'm willing to let delete be O of V. And how big could I let E be? Insert. I need insert to be constant because E can be as big as V squared. So in other words, if I can find a way to delete in linear time and insert in constant time to a priority queue, then this is just going to boil down to V squared. So there's our design goal. We need to find a priority queue representation that will give us O of V deletion and O of 1 insertion. And then we'll have what Dijkstra's algorithm will be linear in that case. Now, you have studied a priority queue in 2420. Does it meet those specifications? What was the cost of insertion and delete min operations? You probably looked at a binary heap representation. What was the complexity of those fundamental operations?
For delete min, and for insertion.
It wasn't constant.
It was log n.
It's log. Because remember, you do a delete min, you take the thing out of the root, and then you have to do a logarithmic operation to bubble up or bubble down in that case. Anyway, bubble down. And so what would happen if we used a binary heap to represent the priority queue here? What would the complexity of this end up being? So we would have V log V plus E log V plus V squared. So it would be O of V squared plus E log V. So in a dense matrix, it would be V squared log V. So oddly, a binary heap isn't the ideal data structure for Dijkstra's algorithm in the case of an adjacency matrix. Now, what about an adjacency list? So there's, again, our term. we've got to do v times delete plus e times insert plus e plus v. So in order to have a linear algorithm, what demands are we going to be putting on the deletion and the insertion operations of our parity cube? What complexity must they have? They have to be constant. And you're not going to be able to do that. You're not going to have a parity cube that lets you do both those operations in constant time. So what we want them to be is the same complexity. Make them as low as possible, but the same. So we know we can do log v with a binary heap, so that's what we'll do. And we end up with Dijkstra's algorithm with a binary heap parity cube as being e plus v log v, so slightly worse than linear. Okay? So what we got to do is figure out where these heaps are coming from. Okay? So let's do that. Let's talk about how to represent an array that gets us that first complexity. So what we're going to use is just an unordered array. So notice, imagine this is a parity cube, and this says A's weight is 2, B's weight is 5, E's weight is 3, and these other things aren't even on the parity cube. So essentially, we're using the vertex as an index into the array. To create the empty array, we just got to store a bunch of nulls in it. To test whether it's empty, somehow, off on the side, we've got to keep track of how many elements there are in there, so we can easily report whether it's empty or not. What's it going to take to do an insert or change operation? So suppose we want to insert f into the parity cube. What do? Yeah, we just go to index f and insert the 4, and we're done. So because we're using the array, the vertex names as indexes into the array or into a hash map, if you prefer to think about it that way, it's easy to go insert it. We just go to the place f is stored and change it to a 4. Okay? What's it going to take to change, in this case, change b to 1? You just store 1. So insertion operation is just an array insertion, array update operation, array store, constant time. Great. Now, what's it going to cost? How do you do a delete min? Right. You have to do a linear search and look for the lowest weight, and you discover it's b with a weight of 1, so you just remove b. What's the cost of that? That's linear. So we have constant time insert / update and linear delete min. You know, if we need to update h, we just do it. If we got to do delete min, we have to search the whole thing. We found out a is the min. Done. That's what we wanted. Constant time insert, linear time deletion. Really easy. So it has the same interface as the next version of the parity cube we'll look at. It's just an internal representation is different. So if we do this, we will have, we'll have a linear time Dijkstra's algorithm on adjacency matrices. Okay. Any questions about that? Yeah.
I guess I understand this, but I'm so little confused why it's faster to have OV squared plus OV squared instead of OV squared plus OV squared. If we go to the previous one, because you were talking about how you wanted V.
Okay. So we've got O of these. So what we're looking at here is the complexity for the matrix representation, JC matrix representation, and this was our complexity of Dijkstra's algorithm. So we've got this V squared term that we're stuck with. That's the cost of just consuming the data structure. So we've got to make sure that this isn't larger than V squared. And we've got to make sure that this is not larger than V squared. If we can do that, then we can eliminate these terms and we still got the V squared. Best we can do is V squared. So clearly, we can let delete be as big as V. And this whole thing will be a V squared term. and it'll go away. What about over here? What was my reasoning that in the worst we would not want to insert to be worse than 1? Yeah.
In the worst case, you can be v squared.
In the worst case, e can be v squared. And so we don't want to multiply by anything bigger than 1, or it's going to dominate that v squared term. Yeah?
Can you remind me again why we consider the matrix instead of just simply using the list, since matrices are always going to be v squared for enumerating?
Okay. He's asking why use a matrix at all, since they're always v squared. We use an adjacent matrix when the graph is dense. When the graph has v squared edges, or omega of v squared edges, then we use a graph. I mean, we use the matrix because it's more compact, takes less space. But the truth is most graphs aren't dense. Most graphs are sparse, so we almost always use adjacency lists. Any other questions? Okay, so then we got the other problem to solve. And so I'm just going to do a quick review of binary heaps because they're needed to solve this next thing we're going to do. So remember that a binary heap is, first of all, a complete binary tree. Okay? What is a complete binary tree? What makes a binary tree complete? Yeah?
All the levels are filled for the tree except the last level is not complete.
Okay. So in a complete binary tree, every level is completely full except possibly the bottom level. And furthermore, on the bottom level, if it's not full, all the holes are on the right side. So you can see here, if you put a right child of 3, the bottom level will be full. It's missing, that's okay because it's the rightmost element. Now, if you stuck something as a right child of 3 and got rid of that 6 hanging out there, it would no longer be complete because the hole's in the wrong place. Okay? The vertices have to be elements that you can sort, basically, you can compare. This is a min heap, so a child's element is no smaller than its parent. So in this case, there are no duplicates, so it's just easy. 2 is less than both 5 and 3. 5 is less than both 6 and 8. So a parent is smaller than its children, or less than or equal to its children. It's not a binary search tree. It's a different ordering. It's a binary tree, but it's not a binary search tree. Okay, to do an insertion, let me just animate it. Let's say we want to insert a 1. So what would be the first step for inserting a 1? Yeah?
Compare each two.
Nope, that's not. Yes.
Put it at the bottom.
Right, you put it in the next available spot on the bottom level. You're thinking of delete min before. So we stick it right there. That's where a new vertex has to go. And then what do? We start trying to push it toward the root. So we compare the 1 and the 3, and the 1 is less than 3, so we swap them. We compare the 1 and the 2. They're out of order, so we swap them. Now we've restored our tree so it's a binary heap. Okay? So let's try inserting 4. Where will it go? Go right there. So again, we got to bubble it up. So we compare the 4 and the 6, they get swapped. Compare the 4 and the 5, they get swapped. Compare the 4 and the 1, no, they're okay. So we're done there. Okay? What's the complexity of an insertion like that? It's log of the size of the tree because at worst you have to push it up to the root, and the trees, since they're balanced, you got a depth of log n. All right. So this is all, this should be familiar stuff. Now what about deleting? Delete min. So suppose we did a delete min operation. How do we do that? Yeah?
Find the minimum of the 2 children.
Well, there's a step before finding the minimum of the 2 children. Yeah? Well, you can't just delete the 1 off the top because now you've split the tree into halves. So what do?
Take the last child and put it up where it should
Right.
be, and then
Okay. So you take the last child. The tree is about to shrink by 1 node, and so the one that has to disappear is the one on the bottom level there, because we've got to maintain that heap property. So we take the 6 away, and we store it at the root, because the 1 is what we want to disappear. So we physically remove the last node in the tree, but we take its contents and store it at the root. All right, so now it's at least shaped properly. How do we get it to look correctly? Someone already said how to do that. How do we get the other heap property? Right. We've got to push it down now. So we compare the 6 to both of its children. And in this case, the smaller of the 2 children is 2, and so we swap the 6 and the 2. Then we compare the 6 to its 2 children. The smallest is the 3, so we swap the 6 and the 3. And then we're all the way to the bottom. Right? Suppose we do this again. What's going to get chopped out? What's going to happen to my tree? Turns out the 6 is going back up. Now we compare the 6, the 4, and the 3. The 6 and the 3 get swapped. Now we compare the 6 to the 9. There is no right child, and what happens? Nothing, because they're in the right order. And again, this is logarithmic time, because the worst that can happen is you push something all the way down to a leaf node. And again, because the trees are guaranteed to be balanced, we always get that behavior. So that's a binary heap. But we have a problem. Our insert operation is called insert or update, which means if it's in the tree, so if we're inserting something that's already in the tree, we have to update its value. Otherwise, we have to insert something new. Now, for that to make sense, there have to be keys and values in this, and I don't have them here. So what's going to be the problem with changing an element? Yeah?
It's not like a binary search tree, so it'd have to be a linear search, right?
Right. The problem is finding the thing to change, because it's not optimized. So imagine those are the weights, let's call them, and suppose that there's a key that goes with each of them. Call it maybe a vertex. So maybe the root is A with a weight of 3, and then B with a weight of 4, and Z with a weight of 6. And you've got to update Q. It's not organized to find Q efficiently. You basically have to do a tree traversal to find a particular vertex to update. But we need to do it in logarithmic time, so we got a problem. We have to find another way to do it.
Binary search heap.
A binary search heap, yeah? That would, if we could have both properties at the same time, that would be nice. Yeah?
I could use min-max.
A min-max heap?
Yeah.
Well, I'll just say we don't need to. I'm not sure if that would work or not, but there's a simpler way to do it. Okay, that's interesting. How would we use a dictionary?
We have the key, and then we have a reference to the nodes.
Okay, so the idea this is just not the right picture. I need something with keys in it. Let me see if I have one coming up. Okay, that's much better. Okay, so here we have a binary heap, but what I've added are, I hesitate to call them keys because a lot of times the weights are called keys. But anyway, we've got the keys, G, E, F, D, H. Maybe I'll call them labels. We've got labels and weights. And suppose we have to update A. So the problem is we got to search the tree to find the A to update it. Once we find it, the update's efficient. What would the algorithm? Suppose you had to change A to a 3. What would happen if, once you found A, what would you do? What would it take? You're decreasing the weight of the 4 to a 3. What would you then do? Yeah.
If you're decreasing the value, then you would propagate it down. If you were increasing the propagate, no.
Other way around. Yeah. So if we change that 4 to a 3, we would attempt to push it up. If we change it to something bigger, we try to push it down. So the problem is finding the thing. So the proposal was create a hash map on the side here, and have the entry for A in this hash map contain a pointer to that vertex right here. And have the entry for G have a reference to this thing right now. So now to do an update, we have to come to the hash map, find the vertex, and update it. And then, but what also happens as you're propagating things, you got to make sure that you maintain this table correctly. So that would work. Yeah.
Would it not also be efficient since we know that when a node is being updated, it's only going to decrease in value?
Well, yeah, if you could put that in the spec. Typically, you're not going to update something unless it's going down. So you wouldn't have to work down in value, which means you wouldn't have to worry about pushing down in that case. Now, the problem with what I just said is you end up with a lot of memory allocated on the heap, with lots of references all over the place. It's a solution that works, but it's kind of complicated. Much better approach with a binary heap is to forget about representing it with nodes and references. You can put a binary heap in an array. So let's take a break and we'll see how that works. Okay. All right, so here's the deal. We can easily pack a binary heap into an array with zero wasted space. So you just see, if you just traverse the tree by level from top to bottom, you see we get the 1B, the 4A, the 2C, and so on. So we can pack it in. And I'm going to use one-based indexing just because it makes the math slightly simpler. The root will always be stored at index 1. When you want to find the child, the left child of a vertex, at what index would it be stored? So let's say that vertex at index 2, which is A, where will you find its left child in the array? Yeah?
You find it one step next into the array.
Not the next step. What is the left child of A?
2 times the
It's
index.
E. So you double the index of the root to get the index of the left child. See, that works for B there. You double the index of B, which is 1, you get 2, which is the index of its left child. For C, it's at index 3, you double that, you get index 6, and that's where the 9D is stored. Where's the right child?
2 plus 1.
You just add 1 to the left child index, so you double it and add 1. Where do you find, if you've got a vertex, how do you find its parent? Just divide by 2, eliminating a remainder. So that works great. And it works much better with caching. You don't have memory strewn throughout the heap. It's all compact into an array. And you can take the algorithm that you're familiar with, and it works just the same. All you're doing, instead of following a reference to get to the parent, you're doing a little bit of math on an array index to find the parent. So let me ask you, why don't we use this for all binary trees? Yeah?
Not all binary trees are complete.
Not all binary trees are complete. What would happen if we had a binary stick? That we just had a chain of right children down 100 levels.
I have a lot of empty arrays.
You would have lots of empty space. Because the root would be at index 1. Let's make them all left children to make this easier. So the root's at index 1. Where's the next thing going to be? Index 2. The next one's at index 4, 8, 16, 32. If there's 100 elements in the tree, the last one's at index 2 to the 100th power. All right? You're not going to find that much memory in the world. So most of the entries are blank. So it only works for binary heaps. It works for binary heaps because they're complete. Binary search trees, it won't work because they can be out of whack. So now we're going to add a second array. So let me show you what we're doing here. The second array is indexed by vertex, or what I was calling label up there, and it contains an index into this array that tells us what corresponds, where A is stored. So to find out the place where A is stored in the heap, you come here to A, it says 2, you go to index 2, and there's A. So that's the analog to the hash map we were proposing. So we've got these parallel arrays. The purpose of that second array is just to keep track of where things are so we can update them if necessary. Now, it makes the algorithm slightly more complicated, but not too bad. So let's do a delete min. Okay? So a delete min says you go to the last spot in the array. Well, that's easy to find. It's the last spot. So I'm sort of animating it in both places. And what do? What's the next thing we do? You eliminate the 1b and you put the 6g over it. So I do that. But what else changed when I did that? Look at the bottom array. So the entry for b disappeared because b is not there anymore. And the entry for g changed from 8 to 1. And so the algorithm becomes slightly more complicated because you've got to keep the, when you move things around, you've got to keep the indexes in the second array updated. And those indexes are just there so that we can do the update later. So then we do the bubbling down. So we compare those 3 elements. We swap the 6 and the 2. And you'll see a swap in the array, and you see a swap in the second array. Or you see a change in the second array when they get interchanged. Now we compare that to its children, and we're done. So it was just strictly array operations being done. All right? So let's now change the weight of E to 3. So we find E. It's stored at index 4 up here. So there we are. And now we can change its weight to 3, and then we can start pushing it toward the root. So we compare it to its parent, swap them, compare to parent, do nothing. Yeah?
So would you also need like a hash map to basically map those the A, B, C, D to
Yeah. So I'm assuming here that A, B, C, D are integers and therefore can index into the array. If this were, if these were arbitrary strings, then just think of this as a hash map instead of an array. Okay? Yeah.
So are we just throwing a null at index 0?
At index what?
0.
Yeah, well, if you want to, you could, okay, so an real array be indexed at 0, which just means that you subtract 1 up here from everything. I'm just used to doing it with 1-based indexing. You could adapt this scheme for 0-based indexing easily enough. All right, so all these operations are now logarithmic time. Yeah?
So this is all assuming that we know what the max size of the priority heap would be, right?
Right, this assumes that we know, well, we assume we knew in advance how big the heap could get. Now, if you don't know in advance how big the heap could get, you can still use this. But when the heap fills up, you have to double its length and copy it over. So it'd be like an array list then. Okay, so that helps us out. Now, I just want to mention in passing, there's an algorithm called Heapsort. I'm not going to dwell on it. But basically, you can take an array you want to sort and convert it into a heap. Okay? So you don't have to copy it out into a tree somewhere. You can, in place, there's a way to convert to a heap. Can you think about what that would be? Yeah?
You just keep taking the child out, find the biggest one, and swap them.
Yeah, sort of. Just imagine, let me go back to where I got something to point at. So imagine you just had an array of numbers here. Or in fact, let's back up. I want an array of numbers. Okay, let's take this array right here. Forget that it's there for another purpose. Imagine converting it to a heap. Well, initially, this thing by itself is a binary heap, right? If it's a binary heap of one node, and then we got a bunch of numbers over here. Imagine doing this. Compare 2 to its... Yeah. Take this 2 and compare it to its 2 left children, and swap the 1 and the 2. I'm not doing a very good job of explaining it. Debating whether to try or not. The idea would be, that's a heap. Now consider a heap that consists of just these 2 elements. Push this 1 as far as the root as it will go. Now treat what's left, these 3 elements, as a heap. Take this 3, push it as far as the root as it will go. Push the next one as far as the root as it will go. If you do that, you'll end up with a heap. And it will take n log n time to build the heap from the array. Now, once you've got a heap, how can you sort?
Pull them in.
Okay? So to sort, what you do is you do a delete min. So think about this second array, this array right here when we did a delete min. So we took the 6 and we moved it over to the first element. What happened to the 1? We threw it away, right? What if we stuck that 1 in that unused space at the end of the array? And we don't consider it part of the heap. It's just using the unused space the heap isn't using. Now we've got the 1 at the end. What will happen when we do another delete min? We take that number and store it just to the left of the 1 in the new unused space. So basically, we do n delete min operations. Our array gradually shrinks, our heap shrinks, and our array grows, and what's left in its place is a sorted array. It's sorted in reverse order. So by building a heap and then doing n delete min operations, that's heap sort, and you can do it all in place. You don't have to have dynamic memory to use it. And it takes n log n time. So, given that you can use a priority queue, like a binary heap, to implement a sorting algorithm, someone tell me the argument that proves that you cannot have a priority queue where insertion and delete min work in constant time. How do we know that's impossible? Yeah?
If you're able to do them in less than that time, or in constant time, then Heapsort would be faster than n log n, but we know that sorts are bounded.
That's exactly right. If delete, so I just showed you an algorithm that does n delete min, n insertions followed by n delete mins and sorts the array. And whether or not you understand exactly how it can be done in place, you should understand how it works. You're basically building a heap and then taking the smallest element out, the smallest element out, the smallest element out. They're coming out in sorted order. If both those operations were constant time, what would the complexity of heap sort be? What would the worst case of heap sort be? O of n. And we already proved with decision trees that's not possible. Okay. Let's look at something different. So that finishes up our coverage of graphs, with the exception of one small topic I want to cover next week. And in terms of the book, we're looping back now to chapter 1, which is about algorithms on numbers. And in particular, what it is, it's algorithms on numbers that lead up to how public key encryption works. So we're going to look at a series of algorithms on numbers. Now, it sounds like algorithms on numbers would not be very interesting, right? You know, you've known how to add, subtract, multiply, and divide for a long time. What's different? Well, one thing that's different is we're talking about arbitrarily long integers. So we played with those around. We played around with those before with parasival multiplication. So talking about numbers that can be really long, and we want to have efficient ways to do things like add and subtract, multiply, exponentiate, and so on. And it turns out that we are going to be all the algorithms we're going to be doing are modular algorithms. They use modular arithmetic. So the first thing we have to make sure is that we all understand what I mean when I say modular arithmetic. So I might ask, what is 7 mod 2? Okay? So what am I asking when I say, what is 7 mod 2?
What is the remainder in the division between 7 and 4?
Okay, one way you can think about it is, if you divide 7 by 2, what's the remainder? So when I ask, what is x mod n, this is what I'm looking for. I am looking for, well, I need to just reveal one more line. I want you to tell me, essentially, take x and add or subtract from it some multiple of n so that you get a number between 0 and n. Okay? So that's a way to describe it without talking about division and remainders. So you're adding a multiple of x to get into the right range. So 4 mod 5. I want a number between 0 and 5, or 0 and 4 inclusive. Okay, so what is 4 mod 5? Is 4 in the right range? Is 4 greater than or equal to 0 and less than 5? Yeah. So that's equal to 4 plus 0 times 5. Okay? 14 mod 8. How do we get 14? What do we do to 14 to get it between 0 and 8? Subtract 1/8 from it. So 14 minus 1 times 8 is 6. What about 101 mod 4? What would our k be? How many, the modulus is the 4. How many moduli do we have to subtract off the 101 to get it between 0 and 4? 25. Right? What about negative 14 mod 8? Just off the top of your head, what is it? Okay, we've got to vote for negative 1. Any other votes? Okay, I've got to vote for 2. Okay, let's see what. In this case, it's negative, so we need to be adding 8s. So we need to add 2 8s, right? If we add 1 8, we get negative 6. Add another 8, we get it up in the right range. So yeah, it's 2. Oddly enough, well, I'll come back to that. What's negative 101 mod 4? Now, we already figured out that 101 mod 4 was 1. So it's tempting to say that negative 101 mod 4 is negative 1. And in fact, the percent operator in Java and C# does exactly that, but it's not the correct definition of mod. No, okay, so what if we added 25 times 4 to negative 101? What would we get? -1. So let's add 4 more. That gives us 3. Okay? So think of modulus like the clock over there. That clock works mod 12. Our calendar works mod 365. Your car odometer works mod 1,000,000 or something. Questions?
So for like so if you take the negative, you can just like subtract the 4. So for example,
Yeah.
101 is 1, so you would take 4 minus 1 to get the negative version.
Right, so that's an identity. If you know that 101 mod 4 is 1, you can compute negative 101 mod 4 just by subtracting this from the modulus. Or another way to put it, something mod 4 and negative something mod 4 are going to add up to 4. C# and Java just, basically ignore the sign, compute the mod, and then negate the answer, which isn't right. In fact, that's exactly what that says right there. Anyway, that's modulus. That's modular. That's what modular numbers are. Now, we'll often use this notation here. X is congruent to or equivalent to y, and then in parentheses off on the side, I'll remind you that we're working mod in. And you can read that in various ways. It means that if you take the x mod in and y mod in, you get the same number. Or it means that if you compute the difference between x and y, they differ by a multiple of n. Or it means that if you divide them both by n, you get the same remainder, something like that. So you tell me true or false. Is 5 congruent to 12 mod 7? Are those the same numbers if you're working mod 7? Yeah. Is 14 the same as 36 working mod 3? Well, what's 36 mod 3? 0. 36 is a multiple of 3, so its modulus will be 0, and I know 14 is not a multiple of 3. So that's not true. Okay?
Yes.
They're both even. Okay? So if you happen to be doing an assignment or an exam, and you're asked, given ridiculously large numbers, to do something like this, there's always some sort of trick. In this case, it's recognizing that they're equivalent mod 2 because they're both even. They're both 0 mod 2. Don't start trying to calculate it. What about this? That's easy to see too because we're also good at dividing by 10. This one's a multiple of 10, that one's not. So they can't be congruent. One has a remainder of 1, the other has a remainder of 0. So it's not rocket science. What's another thing where do you use modular arithmetic all the time when you're programming, even if you don't realize you are? So when you're using modular arithmetic, the numbers kind of wrap around all the time. So if you're using mod 7, you count 0, 1, 2, 3, 4, 5, 6, and then 7 is the same as 0 again. 14 is the same as 0, so you're constantly wrapping back to 0. Does that remind you of anything about programming? You may have screwed up on caddis because of it. Integer overflow. If you start adding 1, you start at 0 and start counting up, eventually it wraps around to negative numbers and comes back to 0. Arithmetic on a computer is mod, if it's a 32-bit integer, it's mod 2 to the 32. If it's a 64-bit integer, it's mod 2 to the 64. All right, so here's some properties of modular arithmetic. There's a substitution rule, and what it's basically saying is, if you have two numbers that are congruent, suppose you want to add x and y, and suppose you have x prime and y prime, which are congruent to x and y respectively, then adding x and y is going to, x plus y is going to be congruent to x prime plus y prime. The same thing goes for multiplication, the same thing goes for exponentiation as long as you're talking about the base. So that can look daunting in symbols, but here's a way you can use it to your advantage. Suppose you wanted to compute 14 times 25 mod 4. One way to do it would be to calculate that product and then compute the modulus of the product mod 4. But we can use the substitution rule. The substitution rule says we can replace 14 with anything that's congruent to it mod 4. And we can replace the 25 with anything that's congruent to it mod 4. Then do the operation. So how can we simplify that 14? That's the same as 2 mod 4. And what about the 25? That's 1. So that's the substitution rule says that's the same as 2 times 1 mod 4, which is 2. Or we could have done the multiplication and gotten the same answer. Okay, what about that? 2 to the 345 mod 31. Now the substitution rule for exponential says that you can replace the base of the exponential with anything that's congruent to it, mod 31. But it looks like anything we replace 2 with would be bigger than 2. Doesn't seem useful. So there's a little trick here. And your spider sense should tell you to be suspicious when you see the modulus is 1 less than a power of 2. Anyone had a flash of insight to see how to beat this down into shape? Yeah?
My thinking is, it's 2 to the 345, it's going to be a very long sequence of 1s, and we can just keep the first so many 1s.
Well, see, that's not quite that. Yeah, we don't have to talk about the binary representation. Yeah?
Can we split the exponential into 2 different terms?
Right. So 2 to the 345 is also 2 to the 5th to the 69. But what's 2 to the 5th? 32. And what's the substitution rule say? We can replace this with anything that's congruent to 32 mod 31. Well, what is congruent to 32 mod 31? 1. So the substitution rule says we can replace that 32 with a 1 and get the same answer. Voila. If you'd actually try to compute this and take mod 31, on a regular old calculator, I don't think you'd get the right answer. You'd have round-off error or something. Okay, it works for commutativity. So addition is commutative and associative and distributed. So but this substitution rule comes in really handy, and we use it a lot to try to simplify things. Okay. If you got to add 2 numbers mod n, how do you do it? So we'll assume we know how to add without the modulus. What's it take to compute x plus y mod n? And we're going to assume that x and y are already in the right range. They're positive and they're less than the modulus. So how would you implement it? Without even doing a division. Yeah?
If they're already within the range, the most that they can be is n over. So you just add them, check whether they're greater than n, and subtract n if they are.
That's exactly right. So this is what we do. You compute x plus y, we know how to do that, and then if x plus y is bigger than n, we don't want it to be bigger than n, we subtract n. So we always want to keep the numbers small. One reason we're doing modular arithmetic is so that our numbers don't get too big. So, great. So 3 plus 5 mod 6 is just 8. 8 is too big, so subtract a 6 and we get 2. You never have to subtract more than 6 because you can't be too big because x and y are small to begin with. And all 3 numbers have log n bits. So n is the modulus. So none of the numbers are bigger than n, so they have log n bits. So addition and subtraction is just log n, where n is the modulus. Okay, how would you compute x times y mod n? First step is just to do x times y. Now what? How do we get the number down? How do we figure out simplify it down to a number that's between 0 and n? Yeah?
Divide by n.
Yeah, divide by n and get the remainder. Okay? So that's what you do. So 3 times 5 mod 16 is 15 mod 6, which is 3. the complexity of that, so again, all numbers are going to have at most log n bits. Multiplication is quadratic, let's say. We actually know better than that. We can do faster, but for now, let's just say it's quadratic. The product still has O of log n bits, and then we have to do a quadratic division. So it's quadratic, log squared of the number of the modulus. Now, are any of you uneasy because I have logs up here? How can I say that if something is O of log n that it's linear? In what world is that linear? Yeah? Well, it's not base n, it's mod capital N. What is log n a measure of? What's that putting an upper bound on? Well, yeah?
The number of bits.
The number of bits. So log of the modulus is an upper bound on the number of bits in the numbers we're adding and multiplying. And so if we can add in log n time, that means the time it takes to add two numbers is proportional to the number of bits. So it's linear. Or it's proportional to the square of the number of bits, which is quadratic. Now sometimes, so you won't see the logs, we will use little n to stand for big log of big N. So in that case, addition would be O of n and multiplication would be O of n squared. So you just have to be careful what you're referring to. Typically for complexity, we want to be talking about the size of the things, not the magnitude of the things. So the size of the modulus, the length of the modulus is the log of it. What I want to do is I want to quickly introduce a couple of topics, a couple of operations. I'm not going to say how to do them. I just want to so that you know what they are. And somehow I've misplaced my marker. So I will do it this way. Come on. Okay, so sometimes I'm going to ask you a question like, what is 2 to the third power mod 3? So what am I asking you there? Basically, 2 to 3 is 8. If we take 8 mod 3, we get 2, right? Now, what we'll find out is, suppose that 2 and 3 and the modulus were gigantic numbers. Billions to the billions, mod billions. That would be very expensive to compute, wouldn't it? To do that billions, some billions to some billions power, and then do a division by some gigantic number. We'll find an efficient way to compute that that doesn't involve first computing 2 to the, we'll find a better way to compute that than first doing the exponential and then doing the division. We'll find a much more efficient way to do that. So that's one thing we're going to look at. The other is, I'll be asking you questions like this. What is the inverse of 3 if we're working mod 5, let's say? What am I asking you there? The multiplicative inverse of 3 if we're working mod 5. Well, what am I asking for in normal arithmetic if I ask you for the multiplicative inverse? Well, I'm asking you for something you can multiply. If I ask you for the multiplicative inverse of 3, I'm asking what can I multiply 3 by to get 1, which is 1/3. It's the same thing here. But 1/3 is not an option in modular arithmetic. Everything's an integer. I'm asking you here, what can I multiply 3 by to get 1 if I'm working mod 5? Okay, so what is the inverse of 3 if we're working mod 5? 2. Because 3 times 2 is 6. Take the answer mod 5, you get 1. So the inverse of 3 mod 5 is 2.
Is it just like 3 mod 5 and then minus 5 minus 3 mod 5? Will get you the inverse?
No.
That's not always true.
No. We will look at an algorithm for getting modular multiplicative inverses. But for right now, all I want you to know is where we're headed. That this is what inverse is. So you may see that on a quiz next week. The answer is not a fraction. It's just, you just figure it out.